Okay, hi. Good evening, everyone. My name is Patrick Hall. I try to lead the interpretability efforts at H2O. So the talk tonight is going to be about interpretability for machine learning models. And to be clear from the very beginning, we're not really going to touch on deep learning. I think a lot of the academic work in this area touches on deep learning. We are much more concerned about, in particular, tree-based models on IID data regarding human behavior. Is someone going to pay their bill? Is someone going to default on their loan? Is someone going to, churn from one phone company to another phone company? Those kinds of problems. So I will say we are very interested in moving into interpretability for deep learning, and if that's something that you are interested in, maybe we would be interested in hiring you. So if you have kind of a substantial resume around deep learning academic publications, we would be interested in talking to you about that if that's something you're interested in, or lots of experience in industry. Okay, so the title of this talk is Machine Learning Interpretability, the Good, the Bad, and the Ugly. And it's titled that for a reason. I think there's a lot of good things going on when it comes to interpreting this certain kind of complex predictive model. And I think there's also a lot of bad and ugly things going on when it comes to interpreting this certain type of predictive model. So I'm gonna start, from a very broad, non-technical perspective, and slowly move into details. And I would say if you have kind of a clarification question as we're going along, just raise your hand. We'll try to clear it up. If you have a kind of longer discussion that you'd like to have, I'll be around after the talk, and I'll be at the H2O booth tomorrow. Okay? Uh-oh. Okay. So this is not a one-man show. Lots and lots of help from lots of very brilliant people. So I'm very lucky to work with a very talented team of scientists and engineers at H2O. And we're also very lucky to work with some of the biggest names in statistical learning as our academic advisors. And we've worked hard enough, or we've been lucky enough, probably some combination of both, that our work around interpretability has been, to a certain extent, embraced by the community, and we've been doing lots of talks and tutorials at various conferences this year and last year, and so that's been great. So I need to ask this, actually. Does everyone here know what machine learning is? Before we talk about machine learning interpretability. I know no one's going to raise their hand and say they don't. Now, I should have asked it. I should have said, who knows what machine? Let me ask. Let's just pretend I didn't say that. Who knows what machine learning is? Okay. All right. So why is what is machine learning interpretability? So, assuming you know what machine learning is, machine learning is this subdiscipline of AI that learns these very complex functions from data that's typically trying to predict or classify or discriminate between different types of phenomenon, right? So the problem is that these functions become very, very complex and difficult to interpret, difficult to explain to your boss how they work, difficult, and when I say difficult, I mean borderline impossible. Difficult to explain to your boss how they work, difficult to explain to your coworkers how they work, difficult to explain to your customers how they work. So they tend to be very accurate predictors, but very difficult to explain. And so there's lots of definitions about interpretability, actually. This is just the simplest one, and I'm a simple man. So this is my favorite definition of machine learning interpretability. So we're looking for a way to present or explain to a human being what the complex mathematical function that's been learned from data is doing. And if you have not read Towards a Rigorous Science of Interpretable Machine Learning, it's not even a long paper. I'd highly recommend it. It's very approachable, even for, say, the business analyst community would probably be able to get something out of it. Very, very crucially, of course, H2O are not the only people working on machine learning interpretability. There's a large group of academics that work under this acronym FAT, Fairness, Accountability, and Transparency in Machine Learning. And they have a great web page that goes into a lot of detail about what interpretability is exactly, why it's important exactly. So I would urge you to check that out. And then another group of researchers, I live in Washington, D.C., so maybe I just run across these people more than you do. Another very prominent group of researchers in this field is from DARPA, the people who brought you the internet. And it's the military, basically. And you can imagine why the military would be very interested in, they're especially interested in deep learning interpretability. They're especially interested in training sophisticated pattern recognition technologies and then understanding how they work and when they might fail. And you can imagine why they might be interested in this. But they tend to call their program XAI, or Explainable AI, and they have a nice website that talks about some of their unclassified goals as well. Okay, so why should you care about this? This is one of my, the quote is maybe a little non sequitur, but I think it's really important. This is not just about helping banks use more accurate predictive modeling algorithms, even though that's basically what the commercial drive is about. In general, right, artificial intelligence promises us more convenience, organization, automation in our day-to-day lives. And as these technologies become more and more important in our lives, we'll probably have more questions about how they work, and especially we'll have questions about when they go wrong, or if they send us to jail, or don't let our kids into college. So there is a very, very important social aspect to this problem. Now, I work for a commercial company. Mostly, I'm interested in helping regulated industries that have previously not been able to adopt machine learning technologies due to heavy regulatory burdens, help them use these very complex predictors. That's my professional goal. I think it's very, very important to think about the ways that these artificial intelligence systems will be impacting our day-to-day lives, and we will certainly want to know how they're making decisions as they become more and more prevalent in our lives. And I think another aspect of this that's very important, we've all seen something about this recently, most likely, as cybersecurity, IT security issues become more and more prominent in our lives, and as machine learning plays more and more central roles in these complex IT systems, it will be very important to be able to debug these systems to understand if they've somehow been tampered with. And it's very, very difficult to do that without having deep insight into the internal mechanisms of the system, whether the systems have been tampered with, whether the inputs of the system are being tampered with, or the outputs of the system are being tampered with. So I think there's both very important social and commercial motivations for this problem. Okay, so why haven't we just been doing this? Well, when was machine learning invented? It was invented in 2006 by Google and Facebook, right? No. Who wants to give an answer? Who wants to give an answer? What's that? Who's got the answer? Who's got the answer? Yeah. I would say 1940s, 1950s, personally. Okay. But you may have other opinions. So it's an older technology. Why haven't we been just doing interpretable machine learning since the beginning? Well, because it's difficult. I'm going to talk about two reasons why I feel it's difficult that I've run into in my undertakings in this direction. And you may run into other problems because I think it is a fairly fraught and difficult problem to solve. So machine learning algorithms create functions that intrinsically combine and recombine variables until they're interacting in very, very sophisticated ways. Okay? So the one goal of machine learning is one goal of machine learning interpretability is to disaggregate a prediction to to form something called reason codes. So if you've ever been turned down for a credit card or even looked at your credit report, the credit rating agencies or the credit lender has to, if they turn you down for a credit card, they have to give you, I think in the US it's 5 reasons why they turned you down. And those are called reason codes. And it's those are related to your input variables that went into their credit scoring model that decided you probably wouldn't pay your bills, okay? So if you're turned down for a credit card, you might see something like your length of credit isn't long enough, your savings account balance isn't high enough, things like this, okay? It doesn't say the sophisticated interaction between your savings account balance, your length of credit history, your debt to income ratio, and 5 other variables are why we turned you down, right? We have to break it down in simple terms, and those are called reason codes. And that's sort of fundamentally at odds with the way machine learning algorithms work. Machine learning algorithms intrinsically consider high degree interactions between input variables, and so disaggregating a prediction into single feature contributions is a difficult thing to do, okay? And potentially even questionable. So one thing to remember is that a lot of these approaches that we'll talk about later are approximate. Some are very approximate. Okay, another reason that I find machine learning interpretability to be difficult is because when we move, so I'm just going to talk loud. So what I'm trying to illustrate here, it's a little advanced, but I think you'll get it. So when I train a good old-fashioned linear model, I'm a big fan of linear models, I'm a big proponent of linear models. When I train a good old-fashioned linear model, that's called a convex optimization problem. And what that means is, given my input data and some numeric value for a parameter for interest rate, let's say for example, and for a model parameter for income, some combination of those model parameters and your input data will lead to the lowest possible error state. And that lowest possible error state, if I was to draw a straight line here and over here, straight to this axis, these would be the values for my income and interest rate parameters in my model. Okay? And you can see there's only one best model. It's not quite as simple as this in the real world, but it's not far from wrong, actually. Now, when I go into the machine learning world, I can actually have many very good models for the same data set. And this is a well-known phenomenon, and it's sometimes referred to as the multiplicity of good models. So for even a well-understood data set, there's many, potentially an infinite number of machine learning models that can give you good predictions. So when I go to explain one of these models, it's very crucial to remember I'm just explaining the one that we happen to be using. The one model out of many, many, many good models for this problem, I'm just explaining one of those, okay? So those are the 2 reasons why I think it's difficult. So why, given these, fairly fundamental problems, why would we even try to do something like this? I do think it's valuable, and this is why. So, good old-fashioned linear models, and actually some aren't even old-fashioned anymore. Linear models tell us about average behavior, and that's great because it's very easy to explain averages. So I like to think of linear models as approximate models, but models with very exact explanations. And if you ever took a college statistics class, you'll probably remember how to interpret a linear model. So here's my linear model, this straight line, okay, and it's trying to model the number of purchases, which seems to go up as someone gets a little older and then eventually start to go back down, okay? The linear model is only able to model sort of global phenomenon, right? So it can really only make this straight line. The straight line does a good job telling us about the average. Basically, as someone's age goes up, they buy more things. but it misses this kind of jump. Let's say this is when someone first gets a job and starts making money, and then it misses this decrease, let's say, as someone retires, okay? But it has a very consistent, stable explanation, and if we know the functional form, or the exact parameterization of the linear model, we can even say things like, for a 1 unit increase in age, the number of purchases increases by 0.08 on average. Okay? And you might remember that from high school or college. Now, with machine learning, if you know what you're doing, you might be able to build a more accurate model that estimates the actual unknown function for how someone's purchasing behavior changes with age a little bit better. Okay? The problem is these models get so complex, they become difficult to interpret. I can't really, how could I explain this line to you, right? I'm like, well, it goes up, and then it kind of plateaus, and it goes up again. Thanks. Okay, thank you. So it's a little bit hard to describe this black line. And what I can do, though, and one technique in machine learning interpretability is to say, I'm not going to try to explain this whole line to you. I'm just going to try to explain little parts that are important. And the way I do that is with a linear model. So you can see I might actually get good insights from these approximate explanations of a more exact model, right? I can now see, oh, the slope is increasing very quickly here, market to these people. Oh, the slope is decreasing very quickly here, maybe cut back marketing to these people, right? So I think there is some intrinsic value here to the explanations, even if they're difficult to make and or approximate. To be clear, I think both of these types of modeling exercises and adventures in explanation are useful. Okay, so how can we do this in real life? Well, I think one of the most important ways to start this is by understanding your data. And there's lots of ways to understand data. One particularly convenient way is through accurate data visualization. So there's lots of ways to visualize and understand your data set. These are just two of my favorites. So I very much like the 2D projections that you're seeing on the left, because I projected a 784, 86, I can't remember, 28 times 28 dimensional data set down onto 2 dimensions, okay? So that gives me a way to actually see and maybe understand things in my data such as hierarchy, sparsity, clusters, outliers, and all of these things are things that would be impacting my model and things that I would expect my model to learn if it did a good job, okay? So basically we're starting from the very beginning and we're saying, I need to get some understanding of my data so I can check that my model understands my data at least as well as I do. Now, the graph on the right is, it has a lot of different names. I call it a correlation graph. That helps us understand the relationships in the data set better. So the graph on the left is about understanding structure that we would hope a model would learn. The graph on the right is about understanding relationships that a model would learn. And again, I particularly like both of these graphs because they put high dimensional information into just 2 dimensions so that we can look at it, which for sighted people is very convenient. And another thing I like particularly about the correlation graphs is I can see high dimensional relationships, right? Just in 2 dimensions, I can see several different groups of variables that are highly related to each other and related to other groups of variables. And these are the exact types of relationships that we would hope a well-trained machine learning model would pick up on. Okay. Another way that machine learning interpretability can be practiced is simply by training interpretable models. And I see people taking pictures, please do, but a link to the slides is on the meetup page. So you're welcome to take pictures, but just the slides are available as a PDF also. So I'm not going to go through all the links on this page, but every link on this page is open source software that's capable of training accurate and interpretable model. So no excuses. There's lots of different things to try. In broad classes, these are decision trees, monotonic gradient boosting machines, which are a personal favorite of mine. We'll talk about that a little bit more later. Monotonicity, I'll take kind of a sidebar here and talk about monotonicity for a second. Monotonicity means that, like, as one input goes up, the output of the model can only go up. Or as one input goes up, the output of the model can only go down. So this is actually, I think this is a huge part of interpretability. I can say to my boss something along the lines of, as age goes up, the number of items that the customer purchased also goes up. I don't have to say it's a very complex relationship. You know, I can kind of leave those details out, but just that one little sentence seems to break down a lot of doors. Lots of new kinds of linear models, and I just did a training at a big bank last week, and I always take, you can probably tell I'm a very sarcastic person, right? So I always show a picture of Gauss in the 1800s and a picture of Trevor Hasty in the 2000s and say, you know, a lot of linear modeling techniques that you guys are using are from the 1800s, while there are options from the 2000s that were invented to address all the shortcomings of the techniques you're using from the 1800s. So just like to point that out.
Nice.
Okay. So also rule-based models, very powerful, non-linear, but interpretable if you can keep them simple enough. Rule fit by Jerome Friedman is something I like to point out to people. That's kind of a hidden gem. And another hidden gem, I think, is supersparse linear integer models. And I don't know of any open source software for this, but these are very, very powerful models. These are these kinds of models that's like, well, the famous one is for newborns, right? And it's about the color of their skin, their respiration, are they crying? And kind of each of these categories gets a number, and then you just add the numbers up, and if it's above some number, it's okay. If it's not above some number, you need to rush them to the NICU, right? And so supersparse linear integer models are very, very powerful kinds of models that I think people should make more, you know, take more advantage of, because they're meant for people to be able to do the calculations in their heads in the field. Okay? So I think they're fairly difficult to train, and that's maybe why you don't see as many open source packages around them, but a very powerful technique. Okay, back to visualizations. So some of you may know one of the advisors that we work with, Leland Wilkinson, is the original author of Grammar of Graphics. So I have direct access to one of the best data visualization minds in the world, and I try to take advantage of it. We have two plots here, and again, I've chosen them because there's lots of ways to do this. I've chosen these two because I think that they are particularly useful. So the plot on the left is what I call a decision tree surrogate model. Some people call them explanatory models. Some people call them shadow models. The basic idea is that they are a simple model of a complex model. Okay? So let's say I trained some big fancy gradient boosting machine with 4,000 decision trees, and it took all night to train, and now I have to go about explaining this. Well, one thing I might do personally, and again, this is an approximate technique. One thing I might do personally is train a single decision tree on the inputs to the complex model and the predictions of the complex model. Not on the actual ones and zeros, did they pay their bill or not, but because I'm not, you could do that as well. That's totally fine, actually. But the thing I like to do is to train a simple model on the inputs to a complex system and the predictions of a complex system. And that way I'm making a simple model of a complex model. And then it's very helpful if that simple model has some kind of convenient graphical form that it can be displayed in, right? And so this decision tree I'm just trying to talk about, I think the mic will come on in a second. So what this decision tree tells me is that pay 0, in this case, in this model, someone's most recent payment status is probably the most important variable in the model. And I can see, basically if somebody pays their bills, they go down this side of the flow chart according to the model, and they end up with a low probability of default. But if someone is more than 2 months late on their first bill, then they go down this high priority, high probability of default side of the surrogate decision tree. So, and again, if something is below or above each other in the decision tree, then I can see that they're interacting, right? So that's a big part of this, is being able to detect multi-dimensional interactions. So I can see that there's some three-way interaction between someone's most recent payment, someone's second most recent payment, and someone's sixth most recent payment. I can't really tell you if that's right or not. The point is, this is a tool that would show this to you so that you as the domain expert could decide if that was right or not. I do really like that. Again, I'll emphasize this combination together. So the thick red line in this plot is something called partial dependence. It basically tells me the average prediction of the model for a certain variable. So when the age is 40, the average prediction of this model is about 0.25, something like that, okay? The other lines that you see on this plot are called ICE, individual conditional expectation. And they essentially show how one row, one person in this model behaves. So this would be a very low probability of default person, and if I take that person and I sort of simulate them having different ages, they stay very low probability of default. What's more, this is all good to see, but the really important thing about ICE is partial dependence can be misleading in the presence of high degree interactions. And so if I see my ICE line sort of crisscrossing with my partial dependence lines, that tells me, hey, this average behavior might be misleading. And then I can go back and check in my surrogate decision tree model to see if there's interactions going on. And of course, you can train it deeper than just 3 levels, right? I just picked 3 levels so it fits in the slide. 5 levels might be good to see these kinds of interactions, something like that. So the key here is using these 2 visualizations side by side to get an approximate overall flowchart of how the complex model behaves, to see how variables behave on average, and then to see how individuals are behaving in the model. And if the behavior for an individual diverges from the average behavior, that's a strong indication that interactions are at play. Okay? So all these visualizations I've shown are ways that I think are good to get peeks into this weird high-dimensional world of machine learning models.
Question?
Sure.
First, second, and sixth, that's an interesting structure to build your decision tree surrogate.
Sure.
Why first, second, and sixth? Why first, second, and sixth? That's all.
Well, so I can't, it's a very good question. The point of this, of all these tools, right, I make tools.
Could you repeat the question?
Yes, sure. The question was, why this relationship between someone's most recent payment, someone's second most recent payment, and someone's sixth most recent payment? So the point of this really is to show you these tools so that you can use these tools on your models, and then you will see these kinds of interactions, and then you, as the domain expert, take this variable out, I need to downweight this variable, something like that. Is that a fair answer?
Sure.
Okay.
Sure.
All right, now we're back to this reason code idea. So, reason codes, and I just don't know people's backgrounds. Reason codes are typically roughly related to the beta X contributions of logistic regression models, okay? So in the linear model, credit scoring world, which for the record, I mean, I think credit scoring at large institutions, not fintechs, but credit scoring at large institutions in the US is one of the most regulated modeling exercises in the world. And I think that's a good thing. And I think that the credit scorers, credit lenders in this case actually deserve a lot of credit because for years they've gone through with the different government agencies and worked to make sure, at least to a certain degree, much more so than other people, that their models are fair, non-discriminatory, and explainable, okay? They're still trying to make money, but they have to jump through a lot of hoops. So now the question is, if I can take a machine learning model that's about 2 to 5% more accurate for some large lending portfolio, that's a lot of money. I can make a lot of money, or I can save a lot of money. But to do that, I have to be able to generate reason codes for why the model made the decision it made. And for you guys, there's 3 decent open source packages for doing this. So one is called Tree Interpreter, one is called SHAP, and one is called Lime. And there's a lot going on here, but the reason codes work by sort of giving the input variables attributions for each decision that's made, right? So if we look at this, so if we look at this is output from Lime, and I think it's about whether a mushroom is edible or poisonous. And so you can see it's sort of ranked the variables, it's given them a numeric contribution, and then used that numeric contribution to rank them in importance in any one given decision. And so we would say the model says that this mushroom is poisonous, and the reasons why are because it has a foul odor, something about stalk surface, something about spore print, something about stalk surface. So these would be the reason codes, and anyone that's actually in banking is like, give me a break. These would be the reason codes for this machine learning model decision. Okay, so we're trying to, for each prediction, we're trying to give an attribution to the input variables. We're trying to disaggregate this very complex function that interacts many variables. We're trying to disaggregate those interactions into single variable contributions for every decision and then rank them. So that I can say, this is why we can't give you a loan. Okay, this is why we turned your credit card application down. This is why we're not letting your kid go to this college. This is why we're sending you to jail. You see? Okay? So these reason codes are important, and I will, there's no silver bullet here. The closest thing I've seen to a silver bullet is SHAP. Okay? Shapley explanations, and I can talk about that a little bit more. Maybe I should talk about that a little bit more. So, Lime, local interpretable model agnostic explanations. Lime can be used on any model, okay? And it's that picture that I showed in the very beginning where I'm fitting a linear model to a very complex function and then using that linear model to build explanations about that local region of the complex function. Now, Shapley is very different, and I may say better, okay? Shapley, but Shapley is really best for decision tree models, okay? So Lime is model agnostic. It just needs inputs and an output, and it can generate an explanation. That's very convenient. In my experience, to get the best results out of Shapley, you really need to be using a decision tree model. And Shapley basically takes a row of data and follows it through a decision tree or 4,000 decision trees and keeps track of which variables are contributing as the row moves down the decision trees. Okay? But Shapley is also, Shapley values go back to game theory. Shapley values are the contribution of any one individual to the outcome of a game. And so this really smart kid, Scott Lundberg at the University of Washington, was able to sort of back all of these ideas about attributing local importance to variables in a model prediction to this strong theoretical framework from game theory. So, and in our testing, these have been the most accurate reason codes, okay? It's still a crazy thing to do, to take a model that just combines and recombines variables literally millions of times, and disaggregate that into individual variable values, how they played into each prediction. But if you're going to do that, and if I'm going to do that, I'm probably going to use Shapley, okay? And another thing, so Shapley is in XGBoost. Who uses XGBoost? So go digging around in XGBoost and you'll find Shapley. I don't know if it's documented yet or not, but that's how we do it at H2O. We just went digging through the deep C++ source code of XGBoost and figured out how to get Shapley values in there. They're in there. They're in there. And there's also a Python package. There's also a Python packages. All three of these are Python packages. I think there's an R package for Lime also. I think any of the, if you are outside of regulated industry, I think any of these are great. And I think you should try them. If you're in regulated industry, my strong recommendation to you is to check out Shapley.
How does that relate to, in random forest, we have the Gini importance. How does that relate
Sure.
to?
So the question is, in random forest, we have Gini importance, and how does this relate to Gini importance? So do you mean Gini importance for the whole model? Because that's what I'm going to talk about next. Okay. I'll try to remember to answer your question. Okay. So there's this older technique that's also very important, very good, you should use it, where we just try to decide how important a variable is in a model overall. Okay, and typically this is called variable importance or feature importance. If you're feeling cool, you can say feature, not variable. If you're at a statistics conference, you say variable. If you're at O'Reilly AI, you say feature. So there's kind of a shorthand to how this feature importance works, which is the higher a variable appears in a decision tree and the more times it appears, it will have an overall more important, it will be overall numerically more important in the model. And then the lower the variable is in the trees and the less often it appears, it will be less important in the model. Okay? So if we go back to the difference between this picture and the previous slide, so we're essentially, in this slide, we want to build this type of plot for every single row. Do you want a more technical answer than that? Because I can. So I'll bring it. So in variable importance, we keep track of how many times a variable is used to split and the impact that split makes on the overall prediction, whether it's Gini or information gain, whatever it is. We sum that across all the trees, and that's the variable importance. Okay? The basic idea here is that I take a single row, and then I track that one row through all the trees in the forest or the GBM, and I keep track of which variables were used for that row. Does that help? Okay. So basically, we want to make this chart for every single row, and the chart can be different for every single row. Okay. This is one of my favorite things to harp on. So sensitivity analysis. That just means putting new data in your model and seeing what it predicts. Okay? It's very, very important. And I think this is a great picture. This comes from a textbook from the mid-2000s that says machine learning is not suitable for extrapolation. So just remember, just all the talks you go to tomorrow that are talking about using machine learning for doing prediction, you're not supposed to do that. I'm just kidding. But it is true that machine learning models can make very strange predictions, especially outside of the domain, outside of the range of the variables that they were trained on. Okay? So I highly, highly, highly recommend that if you are using machine learning and don't want to lose an incredible amount of money, that you test, say, like incomes 10, 20% below what you saw during training, and incomes 10 or 20% above what you saw in training, or negative ages, or ages of 120. There's just, and unless you test it, there's very little way to know, especially in regression problems where you've used a machine learning algorithm like on this slide. The functions try to match the training data, and they will bend themselves into all kinds of crazy shapes to do so, okay? They don't know what happens outside the training data, and if you don't test it explicitly, you might have a very unpleasant surprise. And I'll say this, another thing that I see in practice, I one time caught a customer of ours going through a 30,000 by 30,000 correlation matrix on an Excel spreadsheet. Trying to find hidden correlations before they used a gradient boosting machine. That is exactly backwards, okay? So the reason that you would use a highly regularized machine learning model is so that you wouldn't have to worry about tiny hidden correlations in your data set. So if you are transitioning from the linear model world where you kind of torture your data set to find these hidden correlations that might make your parameters in production unstable, if you're transitioning to machine learning, you can ease up on that and instead do this kind of testing. Okay, because the machine learning model, once it's trained, once you pick that model, 1 out of a million that are good that you're going to use, they tend to be highly stable, especially if they've been regularized, which most decent machine learning libraries allow you to do. They tend to be stable. You don't have to worry as much about parameter stability. You have to worry more about prediction stability with machine learning models, is my opinion. So stop going through 30,000 by 30,000 correlation matrices in Excel spreadsheets, and use Excel to do sensitivity analysis for your GBM models.
Can you reiterate traditional learning?
Traditional?
Yeah, please. I know nothing.
Oh. Let's see. So the type of models that most people still use are highly susceptible, or can make bad predictions when they're used on new data, like out there in the world, right? It gets trained on my laptop, but then I try to go use it to decide if I should give people loans or not, right? One thing that can go wrong with the type of models that people use mostly today is if two variables are too related, okay? But when we switch over to machine learning models, they don't care as much about how much the variables are related, because they're going to try relating them all in all these different ways anyway.
They don't care about the relation.
Yeah, but they can make very crazy predictions. And so you have to test them explicitly to make sure they're not going to make crazy predictions. Like let's say the highest income they saw in a training data set was $400,000. Then they come across somebody whose income is $1 million.
Yes.
So what if I'm, then it shoots out, right? I'm expecting that the line just kind of goes like this. I'm expecting that the line kind of goes like this, but instead it shoots down here, shoots up there. It's something you have to watch out for.
I see.
Okay. So another important thing here is that I've talked about how all these explanatory techniques are somewhat approximate. And it's very important to test them. So some of the original papers, including that, Towards a Rigorous Science of Machine Learning Interpretability paper, a lot of the original papers suggested, and I think this is great if you can afford it, if you have time, suggest basically human trials, right? You train your model, you show them, you show a human the explanations, and then you show a human a new row of data, and you say, tell me what the model's going to do. And if they can tell you what the model's going to do, then we say that's a good explanation, okay? Obviously, these kinds of human studies are very expensive and time-consuming. So there are more automated ways. And something we've pursued at H2O to test our own interpretability software is with simulated data. So we will, it's very easy, we'll manufacture data sets where I know like X1, X9, X4, and X8 are important. And I know the functional form of the model, so I can see for any given row what should be more important. And so we can test them against this simulated data. So I highly recommend that. That's been somewhat successful for us. Another thing I would recommend is to test that these explanations don't change too much, right? So if I perturb my data just a little bit, add just a little bit of random noise in, and I see my explanations jumping all over the place, that's not a good sign, right? So we need to test for stability. So the first one kind of helps us test for accuracy of explanations. The second one helps us test that those explanations are stable. Then the bottom one is just an idea I had, honestly. You could try it if it sounds interesting to you. If I'm some credit rating agency and I basically know what my reason code should be and have known for 20 years for a given for everyone in the U.S., right? Then I can kind of start to see when my new machine learning model reason codes start veering away from that. So if you are working in a business where you have reason codes or local explanations that you trust because you've learned that they're okay over a period of years, then you can use those as a benchmark and kind of slowly move away from those and see how accurate a model has to get before you change away from those existing explanations. Oh, and I should say, it's all in the book. Get a book if you didn't get one on the way in. Okay, so here are my recommendations if you're gonna do this in real life. So just in general, consider deployment. So all those nice little open source packages that I showed, they work really well on your laptop. There's no sense of, okay, I've moved this model off my laptop onto my big secure server and I'm now scoring hundreds of credit card transactions a second and I need reason codes for those, okay? That's a hard problem. We solved it internally just kind of by hook or by crook, and we'll sell you software that solves that problem, so come see us later. But you can figure out a way to do this also. It's just, and this is very typical of open source machine learning software outside of H2O, that it's very difficult I can get the answers I need on my laptop, but when I move it into a production system, I'm kind of left high and dry. So consider that, look into deployment options before you get too deep into this, okay? So if I was going to do this today and I didn't work at a wonderful company like H2O that has their own machine learning library and had a proprietary package that just does all this automatically, I would go to XGBoost and I would train a monotonic GBM, a monotonically constrained GBM, and I would use Shapley explanations. That shouldn't be too hard. That's actually a pretty direct way to accomplish most of the things we've talked about in the slides, okay? It's very important to use both these so local basically means the reason codes, okay? So it's very important to use those reason codes and more global explanatory tools, because sometimes the model's behavior in local regions is just too weird, okay? Because the model will do things, it'll get one row wrong to get 10 rows right. So are the explanations for that row that it got bizarrely wrong going to be very useful? Maybe, maybe not. So it's very important to have these sort of more trusted, older, more well understood global methods to sort of as a backup to the newer, less well understood, potentially more fraught local methods. Thank you. So sensitivity analysis, we talked about sensitivity analysis. That's when you test your model, okay? So this is like production software. It needs to be tested. Something that we like to do at H2O, and I don't know if we made this up or if we read it somewhere or something, called random data attacks. So we just take our systems and just over the weekend just expose them constantly to random data. And we find all kinds of interesting things. So I highly recommend that technique as well. That's not so much about model performance. That's more about, so what happens when a variable that's supposed to be a number is a character, but the model still makes predictions, and then you're using that prediction to make some business decision, right? So random data attacks is a good one that I would recommend. And then we talked about testing. So by testing, I mean sensitivity analysis, and I mean this last slide. In our experience, we are starting to believe that model-specific local explanatory techniques are more accurate. So again, the model-specific techniques they're only able to be used on certain types of models, okay? So the tree interpreter is an example of a model-specific technique. It can only be used in a certain type of model. But we find that those techniques, unlike Lime, which can be used on any type of model, we find that those, if you have the luxury of using a model-specific technique, they tend to be a bit more accurate. All those open source packages that I showed, I don't think they're not being used like the most popular R packages or something like that. They have some fairly noticeable flaws that will become evident to you very quickly. Just for example, when we were trying to do this testing exercise, I couldn't find a single set of open source packages where I could test Lime, Tree Interpreter, and Shapley on XGBoost. We had to just write our own Lime package that actually worked on XGBoost to be able to do that. So it's just, it's nice, it's very nice software, in some cases written by the leading researchers in the field. It's just, I get the impression that not that many people are using it, and if corporations are using it, they're probably fixing, doing their own fixes and keeping them internally or something like that. And then, all right, so this is a good one. So you have to be aware of uninterpretable features. So I go to all these pains to make an interpretable model, but then I have features that are from a 17-layer stack denoising autoencoder, or these features, distance from a cluster centroid in some kind of principal component space or something like this. So you have to also use interpretable features, or your model won't be interpretable. So, you can say, oh, as the middle two layers of this 17-layer stack denoising autoencoder, as that value increases, my model can only go up. Nobody cares. It's not interpretable. Okay. So here's some specific recommendations and observations about Lime. To me, the greatest thing about Lime is it can give you an indication of its own trustworthiness. So you can look at the fit statistics of the Lime model, and if the R-squared is 0.3 and the Lime model is predicting 0.7 and the actual prediction is 10, that's a good indication that the reason codes that the Lime model is generating are not particularly accurate, right? So Lime is nice because it can tell you, hey, this is when I'm trustworthy, this is when I'm not trustworthy, at least more so than other techniques. Lime can fail, and I have examples of this that I can show if people are interested. And our guess is it's just particularly in the presence of extreme nonlinearity or high degree interactions, because Lime typically does not consider interactions, and it's a linear model. Lime is difficult to deploy. So this is, again, this thing like the open source packages are nice on your laptop. They can be hard to use if I'm trying to tell somebody why I'm not giving them a credit card in real time. The procedure for Lime is to pick a point that I want to explain, draw a sample around that point, fit a linear model in that sample, and then use that linear model to make explanations. So that means when I'm scoring new data, when I run my credit card, I have 300 milliseconds to do all that stuff, right? And that just doesn't happen. Okay? So we have a variant of it at H2O that is deployable, where instead of trying to form samples in real time, we just use predefined clusters in the training data. It's just something to keep in mind if you're going to use Lime. And I think Lime is great. I talk to the inventor, Marco, all the time. Another really important thing about Lime is that the reason codes are offsets from a local intercept. So what that can mean is let's say I'm in a local region because I'm rich. And that would be, or in my case, that's not true, but let's say I'm in a local region in some data set because I'm rich. So it's very possible that the intercept of the model will just account for that most important local attribute. And then your reason codes will just be offsets off of that. So you are, that may have been me, I don't know. So you are just, how are we on time? Okay, oh, I need to go, okay. All right, so, are we real bad? Yeah, we're bad, okay. All right, I see, sorry. Okay, so, yeah, so the reason codes are offsets from a local linear model intercept. So just keep that in mind. Always try lime on discretized band features or try lime on interactions, right? If you know that an interaction is important, just try it in your lime model. And then another thing we like to do is use cross-validation to construct standard deviations for our confidence intervals. Sorry, we're getting pretty, this is the part of the presentation for the people who knew all the stuff I talked about for the first 50 minutes. Okay, so here's my recommendation on the other two popular packages. So the problem with them is they can't tell you when they might fail. And that's kind of troubling, right? We don't expect things to be perfect all the time, so we don't know when to not trust these types of explanations. We have seen in particular that tree interpreter does appear to fail with regularized XGBoost models. So if you're using L1 and L2 regularization with your XGBoost models, which is a good idea, your tree interpreter explanations can seem to be numerically odd. And I filed a bug on the tree interpreter repo. They haven't gotten back to me. Shapley does handle regularization, and I think if I was working at a bank or a credit rating agency or an insurance company or a hospital, Shapley's the one that I would go to, okay? Has strong theoretical support, and the implementation that we've looked at seems extremely robust. We have not seen it fail, and we've tried it in very, very sophisticated scenarios. And then instead of being offsets from a local intercept, reason codes are offsets from a global intercept or a global average value, which I think actually makes a lot more sense. So, okay, we're done. Go to this webpage. There's more information than you ever wanted to know.
All right. We can take a few questions because we're going to get kicked out soon. Any questions? Mike, thank you. All right.
Hi, thank you for the presentation. So I actually worked in a case for fraud detection where we wanted to give some explanations on the decision. And you were always trying to give the two sides of the equation. So you typically have a score and it's a gray area. You can have reasons for blocking someone from doing a purchase and reasons for not blocking them. How do you deal with these two sides of the equation where you're not just explaining why you're blocking, but you're also explaining why you might not want to block?
So we in our software just always give both. But
Okay.
I think that the standard practice is to say, oh, the model says this person's really likely to default, so we give the reasons they're likely to default, right? This person's really likely to pay their bills, these are the reasons they're likely to pay the bills. But we just show them all in our software.
Do you deal with situations where you're giving explanations for the two sides that are contradicting in some sense?
Yeah, I just don't, come to the booth tomorrow, I'll show you what we do. I'll show you what we do.
Sure, I will.
We just show all the reason codes, that's all.
All right, two more questions.
So, apart from Lime or Shapley, how is model interpretability being practiced in AI nowadays?
Well, like I said, a lot of the academic research is in deep learning, right? You can go drown yourself in interpretability for deep learning papers on Archive or in JMLR, or NIPS, wherever you want. So if you're interested in deep learning, it's great because there's a lot of academic papers. For, as I mentioned at the beginning, for tree-based methods, rule-based methods, things that tend to be used in commercial practice in New York City, that seems to be being done more by software vendors, and I think I gave the booklet gives a pretty good summary of all the different techniques that people are using.
right, last question. We'll be around for, no, okay. You'll be the last one. We're going to get kicked out. And we'll be around to answer questions in the end. Patrick and Navdeep and our team members are here.
And I'll be at the H2O booth tomorrow morning.
So if there's a question about human life critical, and here we're talking about medical, but also certain scientific, let's talk about launch to Mars, where there are human lives at stake. At what point does the community contribute to the discussion about what that looks like, what exactly that looks like, what the linear model versus the machine learning model looks like, and which that we trust?
So, I think in these really crucial situations, I would just do both. I think that's the best. That's the safest thing, right? That's the safest thing, is to have a very interpretable model, and then a more accurate model, and try to get interpretations of both of them. That's what I would do in that situation.
All right. Thank you, Patrick.
You're welcome.